Hello everyone, Mrs. Lindsay here. Today we're going to talk about coordinate planes, placing figures on a coordinate plane, as well as doing proofs using the coordinate plane. So first of all, let's take a look here and let's actually place a figure on a coordinate plane. So I'm going to take and I'm going to assign coordinates to each vertex, and I'm going to again place it on here so it is convenient for me to find lengths. Let's go ahead and make a couple lines here so we can set up our coordinate plane. I'll go ahead and do that for B as well. But we're trying to make a scaling, so again, no sides congruent, right triangle. Well, if I think about the right triangle portion, since I have an XY coordinate plane here, it's very easy to simply use that as my right angle. Okay, so if I use that as my right angle, so now I have a height and a base of my right triangle, I just now need to make sure that I have sides that are not going to be the same. So if I draw that on here, I'll draw it so it's extended just a little bit. I want to add coordinates to this. Now I don't want to pick coordinates such as 4, 0 because this gives me a length of 4. This only applies to this triangle in particular. I want it to be a very generic figure, so I want it to be in terms of a variable. So I need to pick a variable, and we'll just call that A, 0. Now I need to name this one. So I've named this vertex, now I need to name that vertex, but I want to use a different variable. So I'm looking at two different variables here, because if I use A here, then that means I'm going to have the same length. So in this case, I'll just go ahead and choose B. So it's a different variable there, 0B. And then we do have the origin, and that is absolutely fine. Obviously, that's 0, 0. Okay. So now let's think about how can we draw an isosceles trapezoid on here. So again, we're going to kind of use and center it around the origin. That makes it a little bit easier whenever you're kind of apply that origin to the equation and using your X and Y coordinate planes here. Okay. So if I just simply draw a trapezoid and I need to make sure it's isosceles, so the legs are going to be congruent, I'm going to use this as one of my bases. So I'll just call this point here maybe A0 as well. And then this distance needs to be the same. So from the origin to this vertex, from the origin to the other vertex, that should be the same. So I'm going to use the same variable, but obviously it's in the negative direction on the x-axis, so I make that a negative. Now I'm going to draw a base on the top, and I need to connect those. And in order for this to be isosceles, these legs need to be congruent. Even though that looks a little slightly longer, they should be congruent. All right, so now I need to label these vertices. I can't use the same variable because this distance here is obviously not that distance. So if I went over, let's say, B, then I have to go over to the left in the negative B direction. But I had to move up on my y-axis, again, a different distance, so I will call that C for the height of that trapezoid. Okay. So again, this is a way to place a figure in a coordinate plane, which will make it a little bit easier to find sides and lengths. And in this case, we use 3 different variables. And again, you need to make sure that you use variables here, not integers, for your coordinates. Okay. So now we're going to place an isosceles triangle on a coordinate plane with the vertices P, Q, R. So I'm going to go ahead and graph those. So I have P is negative 2A, 0. Then I have Q, which is OA. And then I have R, which is 2A, 0. Let me go ahead and draw that in. And there's my triangle, okay? And we do know it's isosceles, okay? So if it's isosceles, obviously this is our base. It has a length of 4a, a distance of 4a, because we put it, it's on the x-axis, so we can simply just count. But we know that these would then be congruent, our legs would be congruent, so we know that PQ would be equivalent to QR. So we can use the distance formula to find the length of that. So the length of that, if we just simply do one of them, I'll do QR, which is going to be 0 minus 2a, quantity squared, and then a minus 0, quantity squared, which will give us 4a squared plus a squared. Add like terms there, and then we can reduce, taking out that a, so it'd be a root 5. So that is equivalent to PQ as well as QR. And then we already talked about the distance here of PR. We can simply count it since it is a horizontal line. So that's the first portion of it. Now we need to find the midpoints of each side. So if I find the midpoints here, well, the easy one is the midpoint of PR. So if I do the midpoint of PR, since again it's a horizontal line, I can do the midpoint formula, but obviously it should be the origin. All right, 2a on this side, distance of 2a on that side. And then the midpoints of PQ and QR are going to be very similar. Let me go ahead and start with the midpoint of QR. So that formula is add together your x's, divide by 2, add together your y's, divide by 2. So that would give me a comma a over 2. And hopefully you realize when we then take and find the midpoint of PQ, which has the same length, they are congruent, but now I'm in the negative, the second quadrant, so one of my variables, and specifically x, turns negative, so that would simply just turn your x value of your midpoint from QR negative, and your y value would still stay the same. However, you're more than welcome to actually do the midpoint formula with that as well. All right, so now let's actually go into some coordinate proofs. And when we say coordinate proofs, we're really also kind of referring to paragraph proofs, because that's going to mix together some algebra and explanations. So we're given that GJ bisects angle OGH. So I'm going to go ahead and mark that on our diagram. So that's the first part that we would say. We are given GJ bisects angle OGH. Therefore, angle OGJ is congruent to angle HGJ by definition of bisect. So that gives us an angle. Now what else can we get? Well, taking a look here, hopefully you see that GJ is going to be congruent to itself. So GJ is going to be congruent to JG by the reflexive property. So now we have a side and an angle. Let's take a look at what we can do on this GO and GH in terms of our coordinates. Well, we know H is going to be the order pair 6, 0. O is the origin. And then G is 3, 5. Let's see if we can get GH to be congruent to GO. So to do that, we're going to do the distance formula. Okay, so we'll have GO. The distance of that would be 3 minus 0 squared plus 5 minus 0 squared. I'm going to let you finish that, and I'm also going to let you find GH. So push play when you're ready to check your answers for this, and then we'll finish wrapping up this proof. Okay, so hopefully you got that both the distances are 6. So GO is congruent to GH, and then triangle GJO is congruent to triangle GJH by side angle side. Again, so whenever we're trying to prove triangles are congruent, we're always looking for 3 congruent statements. So even if we're doing a coordinate proof or a paragraph proof or flow 2-column, we're always looking for 3 congruent statements. Okay. So again, when we do another coordinate proof, this is really kind of a mix between a coordinate and a paragraph proof. All we are given on this one are the vertices of each of the quadrilateral, O, T, U, V. And there is one mistake on here. I would like you to correct that before we go any further. This should be angle TOU is congruent to angle VUO. So we're looking at this angle here, VUO, congruent to angle TOU. Okay. So hopefully when I mark those on there, you said, you know what, I'm wondering if I can get something parallel, okay? Because those look like they would probably be alternate interior angles, and which segments or lines should be parallel in order for that to be true. And we hopefully can get TO to be parallel to UV. So let's take a look. How do we prove parallel lines? Well, proving parallel lines, you need to find slopes. So the slope of TO versus the slope of UV. So again, change in Y over change in X. So K over M for TO. Now we're going to do the exact same thing for UV. So change in Y, K minus 0 over M plus H minus H. And yes, the H's cancel out. So again, we get same slopes. Therefore, TO is parallel to UV. By parallel lines, alternate interior angles are congruent. So angle TOU would be congruent to angle VUO. Again, so once we prove that these are parallel, our transversal is OU, so these would have to be congruent angles. Okay, and this concludes the section on coordinate proofs.